Hello everyone. Today we are going to be talking about the anti-cancer activity of a mononuclear Cooper complex. So why to look for new anti-cancer agents? Well, as we know, cisplatin is the anti-cancer agent for excellence. But because of the development of drug resistance and high toxicities, research are looking for more nicer agents for human beings. So let's take a closer look to the chemistry of copper. Copper is part of the group 11 of the periodic table along silver and gold. Copper atomic number is 29 and the electronic configuration is argon 3d10 4s1. If we take a look closely to the electronic configuration, we can see how all the 3d orbitals are filled with electrons, while the 4s orbital only have one, being an exception to the regular electronic configuration for transition metals. In biological systems, the more stable oxidation states for copper are copper plus 1 and copper plus 2. Copper plus 1 have very coordination number of 2, 3, and 4 with linear, trigonal, and tetrahedral geometry. Copper plus 1 also behave as a soft acid coordinating with sulfur and nitrogen. On the other hand, copper plus 2 have also a lot of coordination number, being 4, 5, and 6 the more popular, with a tetrahedral or square planar geometry, a square pyramidal or trigonal bipyramidal, and octahedral, behaving as a borderline and coordinated with nitrogen, oxygen, and sulfur atoms. So let's take a look at copper and biological system. Copper is an essential trace element that is needed for all human beings or living things. In humans, copper is essential to the proper function of organ and metabolic process. Copper proteins have diverse roles in biological electron transport and oxygen transportation. One example of this is the superoxidase dismutase, ACE-OD. As we can see here, coordinating with the copper helps to get rid of reactive oxygen species in our body. Also, copper complexes have shown interactions with DNA. For example, this copper complex with this aromatic system has shown to bind to DNA, causing the disconformation of the DNA and also held as an anti-cancer agent. Also, we have found in other research that copper complexes can induce oxidative damage to DNA. We can see an example here of how oxidative damage can damage the backbone of the DNA. These oxidative and hydrolytical DNA damage cause interest in copper complexes and his potential use as anti-cancer agents. That is why this research right here chooses to synthesize, characterize the crystal structures and also DNA interaction anti-cancer activities of these mononuclear copper complexes that they synthesize. So let's look how they did this research and what can we learn of them. So for the synthesis, they prepare this copper-2 mononuclear compound with a chief base right here, starting for the ligand 1,5 bis, 5 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 this guy right here. In presence of air, this configuration changes to the enol form or the thiol form seen that we have. And after a while, the cyclization occurs. And we can see how these compounds right here close the ring, forming the in zero Schiff base that we want to study with the copper agent. So after they did the cyclation of this ligand right here, they add the copper compound in a copper 2 acetate form and add the 1,10 phenanthroline, this aromatic ring right here, to help to improve the anti-cancer activity of the complex. And we have here the final complex they synthesize. This complex have an oxidation state of copper 2 plus and also coordinate with oxygen and nitrogen, as we can see in this picture right here. For the characterization of the reaction, they use a technique called electrospray ionization mass spectrometry, or ESIMS. The electrospray ionization is a technique to generate ions for mass spectrometry. We can see that we have a ball right here that is applied to the sample in order to atomize and ionize the sample and then run from a mass spectrometry. So for the complex one, they find two major peaks, being the first one at 391 for the complex right here, the copper with the Schiff base hydrate. Also, the other peak they find is the Schiff base hydrate at 3 and 13. And the last big peak they found, it is for the 110 phenanthroline hydrate. So we can see the three big peaks they obtain right here. In addition, as another way to characterize the complex they synthesized, they did the X-ray crystal structure. So they have A and B, then A, the molecular structure of the complex, and B, the packing of the molecule in the unit cell. So they found the copper plus 2 have a pentacoordination with oxygen and nitrogen, forming a slightly distorted square pyramidal geometry. Complex 1 was found to be monoclinic and have two different molecules of 1, as we can see in the A structure, to be present in an asymmetric unit of the crystal along with the half molecule of acetylnitrile and water. And we can see the acetylnitrile and we can see how the unit pack of the complex is. After they synthesize and characterize complex 1, they proceed to do some DNA interaction studies. One of them was the Carl-Timoth DNA study, or well known as ctDNA binding. So what they did was to add to a fixed concentration of complex 1 different concentrations of ctDNA, and then by UV spectroscopy analysis, they measure the absorbance value. We can see on the graph right here how if we add more ctDNA concentration, the absorbance of the complex is reduced right here. This observed hyperchromism suggests intercalative binding, owing to strong staking between aromatic groups and base pairs of ctDNA. So this study right here proves that complex 1 binds intercalative to DNA. Also, through the Wolf-Schimmer equation right here, they plot this straight line and they find the binding constant for the complex one, being this one right here. As we can see, it's a high number to the 5, showing that the complex have a high binding interaction to the DNA. Another DNA interaction studies they did was the PUC19 DNA cleavage activity. And the difference from these DNA interactions to the other ctDNA is that this PUC19 is a commonly used plasmid cloning vector and is a double-strand molecule of DNA. So they treat a fixed concentration of this DNA with different concentrations of complex 1 to see the potency of the complex to cleave DNA. As we talked previously, cleavage of DNA through copper complexes can be obtained by oxidative or hydrolytic pathway. So they designed 2 different assays to see which was the pathway that the copper complexes took. So for the oxidative DNA cleavage, they took the super-cold PUC19 DNA, and they did a different concentration of complex 1 from 0, that is our control right here, to 10 micromolar. And also because the oxidative DNA cleavage has to have the presence of reacting oxygen species, they add H2O2 to the sample to measure if the oxidative cleavage was through this path. As we can see, this is the double-strand DNA called supercoiled, and this is a single-strand DNA, also called nickel circular DNA. As we increase the amount of the complex 1, we can see how the double-strand DNA concentration is decreasing and the single-strand concentration DNA, because of the cleavage, is increasing right here. Being for 8, that is 10 micromolar of the complex 1, the one who show most cleavage of the DNA, representing 80% of converting 80% of CS to NC. We can see right here that this is our control, and we don't have presence of the complex right here, and we really don't see like a bend in that complex. To explain this pathway, they explain that the hydroxyl radical, this guy right here, are responsible for the oxidative DNA's cleavage of our PUC19. When copper-1 species are produced from the reduction of copper-2, superoxidant anions, this guy right here, can reduce HO2, forming this really bad oxygen species, or this hydroxyl radical. In comparison with the hydrolytic DNA cleavage study, they observed also that the double strand of the DNA was reduced to a single strand because it was cleavage of the DNA. However, if we compare both studies, the potency of the copper complex in a hydrolytic DNA is less than the oxidative DNA cleavage. So they conclude that this complex 1 cleave DNA in a highly oxidative pathway, and in a less ways they cleavage in a hydrolytic form DNA. Once they synthesized, characterized, and proved that the complex 1 binds to DNA and cleavage to DNA, the research proceeded to measure the anti-cancer activity for complex 1. So the first assay they did was the cytotoxicity activity of the complex using the MTT assay. If we remember, MTT assay used this tetrasodium dye or tetrasodium salt that is yellow and is converted to purple by mitochondrial reductase and then quantified by UVB spectrum. So if there is being the cell is being dying, our salt is gonna become from yellow to blue, and we can measure the amount of cytotoxicity that our complex 1 is producing. So we show here 3 different assays that they did, and the first one is they test the cytotoxicity of the complex against human cervical cancer cells, HeLa. Also, they use human breast cancer cells, MCF7, and as a way to measure the toxicity for regular human cells, they use these HACAT cells. There are no cancer cells. So we can see from the control without complex 1, these are the percentage of cell viability. For these 2 different cancer cells, there is a significant difference of the cell viability, showing that complex 1 is really killing these cancer cells in an optimized way. Also, in regular human cells, not cancerogenous one, we can see how the percentage of cell viability is higher, proving that complex 1 is selective to cancer cells and have a less toxicity for regular human cells. They also contrast the complex against ciplastin because ciplastin is the cancer's anti-aging complex by excellence. And they found that complex 1 have a higher cytotoxicity from cancer cells than ciplastin. And we can see how they show the major cytotoxicity for complex 1 against ciplastin. They also found the IC50 values, and we can see that the difference is enormous from compound 1 versus ciplastin. Finally, the last anti-cancer assay or activity that they did was the estimation of reactive oxygen species by the 2,7-dichloroDehydrofluorescein diacetate, or H2D-CFDA assay. So this is a common dye that in presence of these reactive oxygen species from not show color, show fluorescence. So through UV studies, you can measure if the complex is producing this reactive oxygen species that is again producing the cell death. So they did that study. They conducted and investigated the ability of complex 1s to induce change in extracellular reactive oxygen species level. So we can see that is the control without any ROS species, and this is the positive control. So they put reactive oxygen species on purpose to see the coloration of the chain. We can see without and we can see with. And also we have different concentrations of our complex 1 and how when we increase the concentration, we can see an increase of the reactive oxygen species appearing. So these prove that actually our complex have an oxidative pathway producing these ROS species that help to the DNA cleavage and the anti-cancer activity. In conclusion, they found that complex bind intercalatives to ctDNA. Also, the complex have an oxidative and hydrolytic cleavage pathway. Also, complex 1 show cytotoxicity against tumor cells and log toxicity, and they also found that complex 1 showed escalated generation of ROS species and oxidative stress is involved in cytotoxicity. The future outlook for Cooper complexes anti-aging agents is bright. So they are studying as a chemodynamic therapy, as a photothermal therapy, as an enhanced chemotherapy, and they use as bioimaging. So it's really promising. And that was all for my presentation. Thank you so much for your time.